That's good for the invite. I'm happy to talk to you guys a little bit about our solution to adaptive and what we do in our clinic. I have the title a little bit backwards. I'm actually going to talk to you about adaptive strategies and our real-time tumor tracking that we have. So our clinic is a small private community hospital nearby here in Lugano, about, depending on the traffic, half an hour south. We're a single LINAC center, and so initially in 2009, when the department was opened, we had a tomotherapy unit, which was then substituted out a couple of years ago with RadExact, which is just a fancy name for tomotherapy, the new platform. But quite the opposite of Utrecht. We're a small, very small patient load, small center. And so for those of you who aren't aware, I guess, of what tomotherapy is, I'm not going to get into a long story, but it's a LINAC mounted on pretty much to a CT gantry that rotates with a couch that translates forward. And so you get kind of a helical treatment. There's been a lot of developments, but today's talk, what I'm going to focus on, obviously, for adaptive strategies is most of the recent software and hardware that's been added on to the platform. And the big one, let's say, was January 2022. So about a year and a half ago, a lot of these additions came on. The big one here that you'll see in a lot of my slides, I have ClearRT. That's the marketing term for KVCT on the machine. And so this was just a published paper a couple of years ago by Glidehurst, which shows the various strategies, workflows for adaptive. But there's three big ones, which, let's say, the processes, which most people know. You have an offline monitoring, which is some idea of slow, gradual deviations from some baseline, your KVCT, and then you're intervening at some point. You have online adaptation, so you have the idea is random deviations, which you're going to be correcting with the patient on the couch. And the idea is usually it's in the SBRT context because of organ at risk dose. And then lastly, your baseline, the KVC, really isn't representative of what you're wanting to treat. You have tumor motion, breathing, peristaltic motion. And so you're taking that into account. And so on our platform, there's two products. There's one which is called Precise Art, which deals with the offline. They have one called Synchrony, which is for real-time tumor tracking. And then lastly, we've created a workflow for online adaptive, which I'll show you. We don't actually do online adaptive. I'm going to kind of show you the workflow, what we do in our clinic. And so when it gets to this offline module, what is it exactly? Patients are enrolled into this module. And so when your doctors approve the plans, you can decide to enroll a patient if you have a protocol, let's say, or during the process of which you want to investigate, you can enroll the patient anytime. Behind the software, you have MIM. And so MIM really is the structure of which is using all deformable image registration and workflows. Every day, your simulation CT with your contours is then going to be deformed onto your daily KVCT for the contour propagation. You have an actual dose calculation onto the daily KVCT because it's not a cone beam, it's an actual KVCT. You get accumulated dose, projected dose. I don't like those at all, so I'm not going to talk about them, and I'll make some comments at the end actually and see what other people think, I guess. But I don't like dose deformation. But the big thing here is automatic report generation. And this is really nice. And this has taken a couple iterations, but recently you can do your user-defined reports. You can put in graphics, trends. You can evaluate the points, or you can be lazy like we often are, and you can just use the dose volume criteria, which you used for the approval of the plan, and it can follow those. And so at our clinic, we had a workflow which was really based off of your matching being done, your image guidance at the machine. And so for the last year and a half, the big work that we've been doing is transitioning to a more objective approach at dose-defined actions at the machine. And you always on the tomotherapy platform, you could actually recalculate the dose on the MVCT at that time, and you could look at it, but it didn't have dose, the actual contour deformations. And so it wasn't as precise, let's say, in what you were actually getting. And so this is much more, it's a nicer offline method. And so we're seeing if we can be more objective of our interventions. And so what I'm going to show you guys a little bit is some of our focus studies regarding this. And so prostate patients, and specifically we were looking at the CTV of the prostate. And inside, once we got this, the big objective criteria that we decided internally after we talked was we wanted to maintain essentially the CT volume to make sure that it gets over 95% of the prescribed dose. Organ at risk doses, we're following, we do intervene on them, but we don't have any objective criteria. This is something still in evaluation. one of the hard points we put for the CT, the prostate and evaluation in this study is that there are 3 consecutive days we wanted to adapt the patient treatment. And then likely I was trying to do some sort of assessment of the deformation quality. Is it accurate? What kind of uncertainties are we seeing in the variability of this automatic deformation? And is it really possible to do this? Because what quite frankly is there's no ground truth here. These are patients that we're treating, and so we're kind of evaluating, let's see what we could do. And so here's just a quick example I'm going to go through with you guys. Pretty common that we're going to see the blue deformed, automatically deformed contours, and you can see that this is the registered KVCT over the planning CT. And you're going to see that there's a systematic pitch, and that's pretty simple. It's pretty common. You have pelvic region patients, which they tend to relax during the treatment, and so you get this characteristic pitch. If you actually though look in more closely, what you're going to actually see is that it's grown as well. And so, is there some edema here? Is this an error in the algorithm? But if you then recalculate, what you notice then is due to this is you have target underdosage in the bladder prostate interface. And so one limit we have is in these plans, and this is why I picked it, is we delineate the prostate bladder interface, the print or the shadow of the prostate on the bladder as CTV. And when this is propagated, if we look a couple slices above, what you notice is it's very hard to define actually in the quality of the image. So here you go. This is for the MR guidance. Yeah, you could probably define this much better, but there's a limit that we're dealing with. Is, does this matter? Should we include this? Should we not include it? It's very hard to tell if that's actually it, or is there's a beam hardening artifact between the femurs due to that, which is something we tend to see. So for about 6 months early at the beginning of this year, we followed 15 of our prostate patients. We looked at their data sets, and then we wanted to see who could what followed and how many of these fractions. So we had 88% of the fractions that met one of the criteria, while about 1 out of 20 failed for the second criteria that we were looking at. Only one patient we adapted due to 3 consecutive. So essentially, as I would say, is our margins were pretty good, and we were able to position the patients well within it. The truth is that we had 2 more patients actually didn't meet that criteria, but we were evaluating them continuously and trying to push them, and they weren't failing very badly. And we were actually able to better their CTV dose coverage. The uncertainty evaluation was more difficult, and you can see this is what we saw as the mean standard deviation, the volume change inside the prostate. So it's around 3 cubic centimeters. That's, if you do an equivalent sphere, it's about 0.5 millimeter. So you go, oh, that's not that bad. But we saw that really the deviation tends to be in certain points. But when you look more closely, this is just one patient. And if I showed you all the patients, essentially most of them show an edema period, which then a slow decline in actual volumes. And so at first we thought we were seeing errors, and then we thought, well, this is probably actually following it, maybe working a physiological process. And more likely it's something that's similar you see in prostate brachytherapy. And so there's a recent publication from last year from actually the MRI Linac and at Royal Marsden, and they looked at their moderate hyperfractionated and their SBRT group, and they saw this change or this edema. Interestingly, though, their moderate hyperfractionation didn't, it plateaued off, whereas we had a little edema with the decrease. But interestingly, it was their SBRT actually started to show, it's only 5 fractions long, but they also saw this peak with the decrease. So we think that we're actually seeing the same effect. They're actually following the volume. It looks like it's doing a pretty good job. So just to give you an idea of the process, it really is, protocolized registration. If people aren't meeting our levels, we go to offline monitoring. With the dose monitoring, then we give feedback actually for an individualized, so we don't have to, is there need really to have to readapt, or can we better position this patient off our standardized to make the dose criteria of the target? If not, we adapt the treatment. So this is essentially what you're doing on online adaptive. You're just doing it faster with the patient on the treatment table. So the question is, could we do it? Can we do it? Accuray, the vendor of the machine, has no official product right now. Right now, they're in development with Limbus AI. So that should already say that they're going away from their deformable image registration. They're now going to AI. But some of the other tools that we have on the platform. So we have a retreatment, again, using MIM. And this allows us to access the contour propagation quickly. It does it very quickly. We still have access to a very fast optimizer. In between standardization of nomenclature and scripting, we're able to do make this process quicker. And so this seems like everything we need to do online adaptive. And so essentially that's what we put together. The details probably don't matter for the actual product itself here, but what we noticed was, we've done internal testing of it. It's very quick. So you can fully re-optimize on these patients very quickly. Obviously, the caveat is how long does it take for the contour adjustment? And this comes back to everything. And so it's really been great discussion. I'm happy for everybody's contributions in this aspect. But so again, we have no online art protocols in my clinic. It's obviously mostly associated with SBRT, like I said, due to the higher risk of giving higher toxicity to your organs at risk nearby. But we only have a small SBRT program, something we're wanting to expand, especially since with the technology we've gotten. Prostate SBRT with Synchrony, this is something I'm pushing. I really want us to begin in our clinic, and my guess is that will be our first candidate for an online program as well. I think it's, as we're seeing, it's a perfect candidate. And so what are we doing off on or replanning? Essentially what we've done, which is for what works for us in our clinic, is we image the patients. When we see somebody with a large difference, we move them off the table. We get our doctors down to review our CTVs, and then we do the process. And then we treat them a couple patients later. So, it's in between. It works for us. But to give you an idea, this is just one perfect example, which was a difficult patient. Here is a patient with your prostate, and this is our planning KVCT. They come in, as everybody can see, with some there. But when you look on the side, what you really see is that there was a whole 1.5 centimeter shift of the prostate. And if you look at the calcifications, you have bony anatomy, which is completely different around. So we have our nurse come down, the nurse removes the air, and then this patient was special. I've never seen this much, difference, but the prostate actually moved and then stayed in position. And so you can see your rectum is in there. And obviously if you're giving an SBRT dose here, you can't, you're gonna have to do some sort of adaptation. But also we didn't like this. So we ended up adapting this patient 5 times with this workflow. So on to real time. So now we're on to the product, which is called Synchrony on the RadExact platform. For those of you who know it, so Accuray produces CyberKnife. And CyberKnife is nothing other than really a Linac mounted onto a robotic arm made by KUKA. It was developed by a neurosurgeon for intracranial SRS, and then it's worked its way into the SBRT world. And it functions by 2 ceiling-mounted X-ray units with then the detectors on the floor. And it provides a stereoscopic imaging, real-time tracking, then in 6 axes can be corrected, and it has 5 algorithms that are dedicated to this. The last 3 are what has been translated onto the RadExact platform. And I say translated because really they're completely different. The technologies are different. They used similar names, but the concept is the same. That's what I'm going to say. And so Synchrony is now the name that's been given to all 3 of these, the respiratory with fiducials, respiratory without fiducials, and then a fiducial non-respiratory motion tracking. Here's our machine when we were getting the upgrade, and you can see the flat panel that gets those here. You can see your KV tube opposite. The Linac is hidden, but you can see the MVCT detector on the other side. And below, then you can see this nice little diagram with the man with his diodes on his chest to get the breathing respiratory waveform, and the camera to see the diodes. But then the information then between the KV images and the LED diode markers comes back into the algorithms to give you tracking, but it's only 3 degrees translation for correction on the RadExact. So it is different from also the CyberKnife. And you have jaw correction in Y in real time, and the MLC is used for the other 2 axes. And also then it's really not, it's a form of stereoscopic imaging, but you have a patient that's moving in the bore, and at the same time, your KV tube is actually rotating with time. And so they're not able to work exactly the same. And so what you have is actually you have statistical modeling, which is predicting the position of where it's going to find the next movement of the fiducial in this case, if you're using non-respiratory motion. And then the model is updated with every radiograph. Otherwise, your respiratory motion, whether it's with fiducials or without the fiducials, what you're really doing is correlating the model of the respiratory waveform to a 3D position, which is then verified. So how is this being used in the real world? This is, from what I could verify, is a list of what people are publishing and actually treating. There is There's a lot more that people are now experimenting with, but they aren't vendor approved, I would say, and probably still haven't completely integrated. But when you have nice, neat algorithms, people want to use them and help patients, and so that's what's being developed. This is what we started with in our clinic. And so we had our first 2 patients recently treated at the end of May, the beginning of June. And we just had our 3rd patient who was presented, who hopefully will be treated in the next couple of weeks. And so respiratory without fiducials. And so to give you a little bit, I guess, of context of how this workflow flows, I'll show you through this patient. And so essentially is we're going to do still a free breathing CT scan, which is used for the actual dose calculation. Then we do a 4D CT scan. And the reason we do that is for the ITV creation, which is necessary for a backup plan. So all the synchrony treatments really is highly recommended is to have a backup plan, because what happens if, especially for a respiratory patient, your model were to break down, the patient's coughing isn't able to complete, the patient has irregular breathing for some reason that day. And so you have to have a backup plan. And so this is already one of the interesting points of the technology, right, is developing a whole protocol, a clinical protocol, how you want to deal with this let's say, risk. And then there's more to this so here's your synchrony plan, here's your standard ITV method. You can see that there's a lot more going on in here. This is pretty simple. We define the CTV, we add on a 3 millimeter margin. There's a PTV tracking volume, which is simply put what they discuss for their algorithm is the visible tumor on a soft tissue window. Okay. But these are completely 2 different treatment volumes. And so also this needs to be discussed and planned, because essentially one is half the other. And so what happens if your backup plan also doesn't meet up constraints, which in this case it didn't. And so our backup plan was slightly over 2 of the ribs constraints. And so we actually had to back off on our backup plan. For the 55 gray, we could only meet around 47 gray for in the 5 fractions. But so, these are all things to take into considering due to how this real-time process has been developed. So you have your plan, we have your synchrony plan. What do we do next? We have to define then these imaging angles that we're going to use for the verification during the treatment. You can see here they have something that they call a score wheel, and the score wheel you can drag and you can see how it looks on there, and then you hit validate. You can do 2 to 6 angles per rotation for the machine, and the validate then gives you a thumbs up. Yes, we can follow this. What's it doing in there? We'll get back to, but it's essentially doing an evaluation of the gray values right in the pixels here, but it's proprietary. This is not something that they share with you. At least I haven't seen. And when I asked with people inside the company, I wasn't given any good information. So this is an interesting aspect of really what it's verifying here. So then now you have your angles you want to use, you have your plan, you go to simulation. So at simulation, this is what you're going to see at the operating station. This was actually during that patient's treatment, but it's the same for simulation or any subsequent treatments. Because essentially what you're doing in simulation is giving the treatment, but without the beam on. You're just following and making sure that this patient's able to be tracked. And so in the top here, you can see your LED signals, so you can make sure everything's online. There's no problems with your LEDs. In the main part right here, you can see the KV images, which are continuously repopulating. You can also see that the centroid in this case is being followed. And then maybe one of the most important parts is per angle, you get this measurement difference, which is the actual measurement difference between what is expected in the model and what it's actually seen on the KV detectors. Down here, you have your respiratory waveform, and for image sampling, making sure that you haven't introduced aliasing, because if there's aliasing going on there, you need to do something about it, because you could be incorrectly tracking. This is a good point to follow up if I could speak about. And then lastly is tracking statistics. The main points are here. You can get some nice real-time graphs, and these tracking statistics, which can be then thresholds such that the machine is intervening and stopping automatically the beam on. Maybe the most important ones right here at the rigid body, because everything is based off this assumption that you have a rigid body, and so you're just translating the treatment up and down or where it's moving. But what happens is if it's elastic, well, you have to define then the limits of how much elasticity are you allowing in this treatment, above which then it can actually turn off. Likewise, like I said, the measurement between what was actually verified in the model. And then lastly, the potential difference, which is also, I think this is very nice, it's an idea of the uncertainty in the model, which is expressed in the millimeters. And what's really nice about this gives you an idea actually about your PTV margins that you're using. So if you see this go up on a patient, which you've used 3 millimeters and it's gone over 3, you should probably rethink your PTV margin. So we've now seen what it looks. So we hit build model. It takes maybe up to 20 seconds, usually less for us it did for our first patients. After it's built the model and says, yeah, I'm tracking it. I see the model. I built a respiratory model. Go ahead. And then you hit either simulate and you simulate the patient, or you hit treat. And then at any time you can pause, or if it intervenes, you figure out what the problem is and you continue to treat. Okay. But that's not all. Behind the scenes, then there's even more. So there's more parameters that need to be defined. And this is the bread and the butter behind the algorithm, right? Is tracking range and the sensitivity of this evaluation, which it's going on about saying, well, I really did find that fiducial, and this is where it is, or this is the centroid of your volume, right? And so you can either have say, I want a low event score, which I allow to go on, or a higher, right? Delays, how much time are you going to allow? Because what happens if the patient starts to breathe irregularly, let's say, and go outside of the limits, because this can compensate up to 3 centimeters of up and down inside the respiratory motion. So what happens if they go outside of the 3? Will you allow it to treat for that, fraction of a second or not? Or do you want it to intervene? So in conclusion, what I wanted to say is, well, as we've seen, it's soon to be ubiquitous. We're a small center in Lugano, and I have the capability essentially to do all 3 of these. And I think every vendor now has products, and if they don't have products, they're in the midst of releasing them. So it really is, adaptive is present. I think offline art is underrated, and it plays a huge part in confidence of what you're doing. And so no matter what you guys are developing, I think that this is really important to seize the offline process and how it overlaps with the other 2, online and real time. I think the biggest point from my experience in the year and a half that we've had this is online. You can be quick all you want, but that's not the problem. The problem is the organization and the resources. And I think the RTT solution is fantastic. I don't know how you guys got that to work. And I mean, it's a lot of work. And I mean, just the communication level between RTTs and doctors and us and what we've been developing for the last year and a half, it's very hard having people on vacation who are maybe more qualified, having people who's substituting, and are these information passed on? How is this information being passed on at the operating station? These are the points that really matter. And then lastly, I'd say is real-time art is going to be solved in various, every single, technology is going to have a unique way. And each one of these is going to require in-depth understanding. I mean, and a lot of preparation. So I was told, I'm giving the talk to a lot of PhD students and to show limits. And so I wanted to use some provocation. So our processes are not discrete at all. And there's overlap in all of these. And I guess to me, it's the overlap is the fun part. It's when you're in there and you're understanding how they overlap and how they interact that really matters. And if you're developing something, it's also how you make something that's useful in the clinic and it gets used and it is successful. Is technology limit or we? I may say the latter. So I'm glad everybody was talking about this. There's so many examples you could give. The RTT is really becoming the point of the knife is one, but statistics, models, and uncertainties. The world is becoming this, and are we good? Are we humans good at understanding these things, especially on the fly? Because things are going to, AI is coming in, things are going to be quicker. Are we really able to assess what we're doing in the moment? And so again, what you're developing, probably tools to help us to understand, is going to be really important. I hate dose accumulation. I just think it's wrong. And so we need to adapt our thinking and how we're evaluating these things. Everything's going to extreme hypofractionation, SBRT, single shot. We're noticing we can do this safely. We're seeing the benefit clinically. I think there's a whole idea of, kind of like Heisenberg's uncertainty principle here, but we're not there yet. But the idea is, can we really understand what the dose accumulation is, and do we really need it anymore? So I won't go more into that. But if you just think about tumor progression in biologically guided radiation therapy. And lastly is, how are we documenting all this? Everybody's doing different things here. And if we're trying to evaluate, we have to somehow figure out such that an MRI LINAC can be evaluated in the same aspects that, a rad exec is. That's everything. Thanks.